one of the problematic features of the current picture is that it's very, very hard to come up with a viable alternative that you can actually test. So, that coupled with the fact that we have only one universe, I mean, to me, it's very, very problematic to say that we have a very good functioning. So I think, I would be comfortable saying that we have a very, a theory, a framework that describes the complexity as we see it in the observations, in the observable universe at the moment. But I wouldn't, I wouldn't go as far as saying I think we've zeroed in on the correct theory yet. But I think it's also very hard to see how you could actually test a completely different theory. So there has been one proposal. There has been one proposal, which I haven't shown you here because it turns out that a lot of a relativistic version of that theory is not sound. It's not correct. It's called TEVS. It's a tensor vector scalar theory. It's Motti Milgram and Bekenstein who've come up with it. And they have offered some tests on small scales that kind of work. So for example, that theory can, without the use of dark matter, explain galaxies and the behavior of galaxies, the measurements of the rotations of stars and galaxies, but it fails in describing lensing. So it's worthwhile to mention as an attempt, but it just doesn't work. But that doesn't mean that that's evidence for dark matter. Okay, it's just that it's very hard to come up with a theory. And the problem with that theory is that calculating. Okay, it took 10 years for them to figure out how to calculate light deflections. So in such a theory to compare with observations. And they recently came up with a formulation, but it turns out it doesn't match anything that we see. So that's what I mean. So the alternative, and that was dispensing with dark matter entirely. And it turns out that in order to describe and match clusters, they actually needed to add in neutrinos with a lot more mass. So that sort of destroys the basic idea of why you're... So in some sense, the evidence for a model that looks like this and has a lot of features that this model has are mounting. But whether it is this, I think we will never be able to tell because of how we assembled this model. And to me, that's problematic. And I think there's some very, very interesting issues that I hope some of you will get more interested in engaging, rather than just sort of being excited only about the multiverse and bubbles and, because I think that, in the stuff that we have a lot of data for, there are lots of unresolved, interesting problems. So I'll stop here and I'll let Branden take over.
Take a 2-minute break. Collect a large n, and that's intractable. It seems to me that's why you need to do simulation. These are just minor points. More major point, which is what my comments are mainly going to be about, are experiments epistemically privileged over simulations in general? And if so, why might that be? Priya suggests that experiments have a materiality that gives them epistemic privilege. I don't agree with that. And that's mainly, I'm going to talk about an alternative. The work of Wendy Parker and Eric Winsberg has been really influential on me on this point. Wendy Parker has a paper, there's the references at the end of the handout, where she argues that materiality is not, if there is something epistemically privileged about experiments, it doesn't have much to do with materiality of anything. And that's because simulations are material. They're we're talking about computer simulations here. You're interacting with a material object, a computer, which you're using to then make inferences about a target. And you can imagine computer simulations of some silicon, silicon target system, silicon-based target system. The fact that there's a material similarity, I don't think that's really what's doing the work. I'm going to try to talk about what I think is doing the epistemic work. I think there is an important epistemic difference. And here I'm just going to borrow from what Eric says in a recent paper, largely. So this is just background. Third thing that I flagged, she kept saying these models aren't falsifiable. one reason she pointed to was that there's only one universe. Maybe I'll come to that at the end. I'm not sure why the uniqueness is a problem. Again, in historical contexts, all the events are unique in some sense, but I don't think that means that historical theories or explanations aren't falsifiable. Another thing you might wonder is, and this is more relevant to what I'm going to talk about, how are simulations implicated in the non-falsifiability? That I don't really see. If there is a problem with falsifiability, I don't know how the simulations here are implicated in that non-falsifiability. And you might just have a more general worry. Are historical explanations or historical descriptions ever falsifiable? I mean, why are we worried about that? Okay. Again, these are just background. And finally, two things which will come up more in the comments. What role precisely do the simulations play in this very complicated process of model building and testing? And so I'm going to invite Priya to talk more about that. And finally, there's this thing about, she emphasized there's this special experiment that doesn't depend on certain assumptions about the relation between matter and light. And she really liked that experiment. She thought there was something epistemically privileged about that. I think that's interesting because I think it plays into a view that Eric has about what makes, what's important epistemically here about simulation. So I'm going to come back to that at the end. Okay, that was just from my notes. Now, because I don't accept the materiality difference, I don't think that's what's making the epistemic difference. I'm going to need a different view of how to think about the epistemology of simulation. And here, I'm just going to borrow largely from what Eric says in a recent paper, A Tale of Two, I think it's A Tale of Two Methods, actually. So the point he makes there is that simulations and experiments both involve inferences from the observed behavior of some physical object system to some other physical target system. And the crucial differences here are going to be epistemic, not so much metaphysical. They're not, at least that's the view I like. And the real question is just this: what's going to ground, and this is a quote from Eric, the argument for the suitability of using the object system to stand in for the target system? So the object system might be a computer simulation running on a computer, and the target system might be the universe or some part of the universe in the case of cosmology. Or you could imagine that the object system, it could be a computer simulation of fluid flow, or alternatively, you could just have a tub of water where you're doing experiments with fluids in a small scale, and you wonder how that'll scale up. That's, that's also another kind of case that you might think about. But in all these cases, you have some physical object system supposed to stand in for a target system. And then the question is, what grounds the suitability of that standing in relation? And the idea, which I like, is that the thing to focus on is that the difference between experiments and simulations, the key difference is that different background knowledge and different background assumptions are involved in grounding this argument for suitability. So here's what's supposed to be distinctive, and I kind of like this way of thinking. Simulations are investigations in which, this is a quote from Rutgers, in which the choice and configuration of the object system, so in this case maybe the computer simulation model, is guided and constrained by principles taken to be reliable for building dynamical models of the target systems. It is constitutive of simulation, on this view, that it's the purported reliability of those principles for model building that provides the background for belief in the external validity of the investigation, whether it be, in this case, it's a simulation, but you'd have the same, you'd be asking the same question: what background beliefs or knowledge do you need to ground the suitability of the object being used as a stand-in for the target? So the point is, if this requisite background knowledge is secure, then simulations can be epistemically equal to or even superior to experiments. For instance, think about simulations of planetary motions. Those are pretty epistemically good. And if you had a tabletop model with, I don't think you would do better with a tabletop model than you're going to just do with computer simulations of planetary motion.